Okay, class, in this lesson, we are going to learn 3 different ways to determine if triangles are similar to each other. Okay, so let's go ahead and get started. The first theorem, called the angle-angle similarity theorem, basically says that if two of the angles of a triangle, so in this case angle A and B, if those angles are equal to two of the angles of another triangle, so in this case angle D and E, so if they are equal to each other, then the triangles are similar. Okay, so angle A is equal to angle D, and angle B is equal to angle E. So if both of those scenarios happen, then the triangles are considered similar. So let's take a look at an example to demonstrate this theorem. So here we have two triangles, triangle DEF and RST. And the question is, are these triangles similar? Well, according to the angle-angle similarity theorem, we would need to find two sets of angles that are equal to each other. So we have one set, angle E and angle S, they're equal to each other. So that takes care of one set. Now we have to find a second set. Well, you see that angle F is 55 degrees, but angle R is 40 degrees. They're not equal to each other, so we would easily conclude that these triangles are not similar. However, that would be an error because we also need to take into account the angle of the third angle, okay? And so we know that the sum of the angles of a triangle add up to 180 degrees, okay? So if we subtract out 85 and 55, so subtracting 85 and subtracting 55, we see that the balance is 40. So that tells us that angle D, angle D is actually 40 degrees. Okay, so now that we know angle D is 40 degrees, this matches angle R, which is 40 degrees as well. So now we have two sets of angles that are equal to each other, and therefore we can conclude that triangle DEF is similar to triangle RST. Okay, so that's one way. A second way is with the following theorem, and this is the side-side-side similarity theorem. Okay, so unlike the angle-angle where the measures had to be equal to each other, here with the side-side-side, we are looking at proportions. Okay, now when we look at proportions, we have to make sure that we follow the order of the way that the triangle is named. Okay, so in other words, here we've got triangle ABC, which is this blue one. Okay, and then triangle DEF, which is this magenta one. Now, if we take a look at side AB and we want to compare it to the corresponding side of triangle DEF, we have to take a look at AB, which is the first two letters of the first triangle, and so we have to compare that to the first two letters of the second triangle. Okay, and that's why we have AB over DE. So that's the first proportion. The next proportion is side BC, okay, and that happens to be the second and third letter of this triangle, and so we have to compare that to the second and third letter of the second triangle, and so that becomes EF, and that happens to be this side of the triangle. Okay, and then the third side is AC. Then that represents the first and third letter of this triangle, and so we have to compare that to the first and third letter of the second triangle, which happens to be DF. Okay, so if all three of these ratios are equal to each other, then both triangles are similar. If two of the three ratios are similar, then they are not similar. If two of the three ratios are equal to each other, then the triangles are not similar. Okay, so the requirement is that all three ratios have to be equal to each other. So let's take a look at the following example that takes into account the side-side-side similarity theorem. Okay, So here we've got triangle ABC and triangle DEF. And the question is, are they similar to each other? Well, let's go ahead and set the proportions correctly. So we're going to take AB, which happens to be the first two letters of that triangle. So we're going to say AB over the first two letters of this triangle, which is DE. So AB over DE. And the question is that equal to BC over EF? Again, BC is the last two letters, so we have to compare that to the last two letters here. And is that equal to AC, which is the this is AC here, and this is the first and third letters. So we have to compare that to the first and third letters of this triangle, which happens to be DF right here. So is that proportional to DF? And then once we excuse me, set those proportions correctly, now we can replace each of these segments with their corresponding values. Okay, so we know AB here says that it's 10. So now we're going to set that to 10, and DE happens to be 15. And the question is that equal to BC, which is 6, and EF, which is 9? Okay, BC is 6, EF is 9. And is that equal to AC, which is this part of the triangle, that's 12, over DF, okay, DF, which is this part of the triangle, over 18. Now, if we reduce each of these proportions, okay, and factor 5 out of the numerator and the denominator here, this reduces to 2/3. And if we do the same thing with 6/9 and factor out 3 out of the numerator and the denominator, this also reduces to 2/3. And lastly, if we reduce this ratio by factoring out 6 out of the numerator and the denominator, that works out to 2/3. Okay, so all three of those proportions or ratios are equal to each other, and so we would say that these triangles are similar to each other. Okay, now the third way is called the side angle side similarity theorem, and this is kind of the combination of the first two, in that if one set of the angles are equal to each other, so here we've got angle B and angle E are equal to each other, and the proportions of the sides that make up the angle, so AB over DE, if those proportions are equal to BC over EF, okay, if those proportions are equal and the angles that make up, that are in between those sides, are equal to each other, then those triangles are similar. Okay, now what I'm trying to explain here, and I probably didn't do it very clearly the first time, is that when you take a look at these angles here and they're equal to each other, you have to compare the sides that make up the angle. Okay, it's not just any random two sides. It happens to be the two sides that create this angle. So those two sides have to be compared to the two sides that make up this particular angle. Okay, so let's take a look at another example that supports the side angle side similarity theorem. Okay, so here the question is angle ABC similar to, triangle ABC similar to triangle DEF? Okay, well, we have angle B and angle E equal to each other. So we would say that angle B is equal to angle E. Okay, so that's the first requirement. So that's done. Then we have to take a look at the proportions of the sides that make up this angle. Okay, so AB, and remember we have to follow the order of the way that the triangle is named. So AB happens to be the first two letters. So we have to compare that to DE, which is the first two letters of that triangle. So is AB over DE equal to this side, which is the other side that make up this angle, BC, which happens to be the second and third letter. Okay, so we would write BC over the second and third letter of this triangle, which happens to be EF. So we write EF here. And the question is, are those proportional to each other or equal to each other? So let's go ahead and replace the values. AB is 5. So we'd say that that's 5 over DE, which is 10. And is that equal to BC, which is 3, over EF, which is 6? Well, 5 over 10 reduces to 1/2, and 3 over 6 reduces to 1/2. And so because those proportions are equal to each other, and the angles B and E are equal to each other, we would conclude that triangle ABC and DEF are similar. Okay? All right, let's take a look at one other example where we apply one of these theorems, similarity theorems. Okay, and the question here is, what is the length of MN? Okay, what is the length of MN? Well, before we can determine that, we have to figure out if triangle JKL is similar to triangle LMN. Okay. First, we need to recognize that angle JLK, so this angle right here, is equal to angle MLN. Okay. Both of these angles are equal to each other because these are vertical angles. Okay, and vertical angles are equal to each other. So we have a set of angles that are equal to each other, and we have sides that are proportional to each other. Okay, and how do we know that? Well, see this double hash mark, this says it's 75, so this double hash mark is also 75. Okay, and then on the other side we have a single hash mark, and we're told that the length of this side of the triangle is 1, and so the length of the opposite side here is also 1. Okay, now the ratio of this triangle, this side, 1 to 75, is the same as the ratio of 1 to 75. Okay, and since those ratios are the same, then we would say that triangle JKL is similar to this triangle LMN. Okay, so now that we've established the fact that both of those triangles are similar, we can use that fact to solve for MN. Okay, so to solve for MN, we can establish the ratio. We would say that 1 to 75, so we'd say 1 to 75, or 1 over 75, is equal to MN, and we're going to call MN X here. Okay, so that's going to be equal to X over, well, what is the corresponding side on the large triangle? That's JK, which happens to be 10. Okay, so that's X over 10. Now to solve for X, we're going to cross multiply. Okay, so we're going to multiply these together, which means that's 75X, and we're going to set that equal to this cross multiplication, which is 1 times 10. Okay, that means 75X is equal to 10. And then to solve for X, we're going to divide both sides by 75. And when we do, the 75s cancel out on that side, and so we have X is equal to 10 over 75. And punching those values into the calculator, we find that X is equal to 0.13. Okay, and that happens to be the length of side MN. Okay, hopefully that made sense. If anything was unclear, I would recommend that you go back to the beginning of the recording and listen to this again. Thank you.